The ideal electrical grid operates on a perfect, continuous sine wave, a pure 60 Hz alternating current. But modern industrial production relies on precision. The standard AC induction motor requires exact speed control to match fluctuating load demands. Otherwise, it wastes massive amounts of energy. Engineers achieve this efficiency using variable frequency drives, or VFDs. These controllers take the incoming AC power, rectify it into a flat DC voltage, and then electronically reconstruct a new variable AC waveform to dictate the motor's exact speed. The problem occurs during that first rectification step. A standard VFD uses a 6-pulse diode bridge to pull power from the grid. It does not draw current smoothly. Instead, it siphons power when the incoming voltage wave reaches its absolute peak, pulling current in sharp, concentrated bursts. Look at the trace. Instead of a smooth curve, you get jagged, discontinuous spikes. The waveform is heavily distorted. This represents a direct mechanical-electrical trade-off. By controlling the motor with high efficiency, the VFD injects nonlinear current distortion back into the supply grid. To understand exactly how that distortion behaves in the grid, we have to deconstruct it mathematically. Any periodic distorted wave can be broken down into a series of pure, perfect sine waves using Fourier analysis. By applying a fast Fourier transform, the jagged current wave separates into frequency components. The largest is the 60 Hz fundamental. Smaller harmonic spikes appear at precise integer multiples. Even and triplet harmonics cancel out, leaving the 5th, 7th, 11th, and 13th. The sharper and more erratic the original current wave is, the higher the amplitude of these specific harmonic frequencies will be. Harmonics exist as physical high-frequency currents that flow backward through the circuit, polluting the entire shared electrical system. Industrial equipment like transformers, heavy-duty circuit breakers, and thick transmission cables are engineered explicitly to carry 60 Hz power. They are not built to endure 300 or 420 Hz currents. As frequency increases, alternating current experiences the skin effect. The current is forced away from the center, crowding along the outer surface. This reduces the effective cross-section of the wire, increasing electrical resistance and generating intense heat. Inside a distribution transformer, this excess heat bakes the insulation surrounding the copper windings. Under chronic high-frequency thermal stress, that insulation degrades, guaranteeing premature failure of the hardware. Furthermore, as these harmonic currents flow back through the system's inherent impedance, they create unwanted voltage drops. This deforms the actual supply voltage waveform, pushing instability onto every other piece of equipment connected to the local grid. If the facility utilizes power factor correction capacitors, the situation can escalate into harmonic resonance. The system's inductive and capacitive reactances can align to amplify specific harmonic frequencies, multiplying the current far beyond the hardware's rated limits. Harmonic distortion imposes a constant thermal burden on the system, bleeding efficiency through heat waste while degrading the physical reliability of all connected infrastructure. To manage this pollution, engineers must measure it accurately and enforce strict limits on what a facility injects back into the utility grid. The most common metric used is total harmonic distortion, or THD. It calculates the ratio of all harmonic components present in the system against the fundamental current currently being drawn by the load. Engineers separate this into THDI, measuring the current distortion created by the nonlinear loads, and THDV, measuring how severely that current has deformed the overall supply voltage. But calculating current distortion this way contains a mathematical flaw. Look at the equation. It uses the instantaneous load current as the denominator. If a facility's motors are idling or running at low capacity, that denominator shrinks. As it drops, the resulting THD percentage artificially skyrockets into severe warning zones. This mathematical quirk makes THD an unreliable indicator of the actual physical stress being placed on the utility grid, especially for systems with highly variable power demands. A seemingly catastrophic 60% THD reading while a motor operates at 10% load actually produces far less destructive harmonic current than a 15% THD reading at maximum load. Because of this vulnerability, the primary standard governing power quality at the point of common coupling, IEEE 519, requires a more stable approach. Rather than looking at instantaneous distortion, IEEE 519 dictates limits based on total demand distortion, or TDD. TDD calculates the ratio of harmonic current against the maximum demand load current of the facility. By locking the denominator to the absolute peak capacity the system will ever draw, the metric becomes stable. This eliminates the false alarms triggered by idling equipment. TDD isolates the true volume of harmonic current leaving the facility, providing a highly accurate measure of the burden placed on the upstream transformer. The strictness of the TDD limits applied to a facility depends on the grid's short-circuit ratio. A stiffer power supply with a high short-circuit ratio relative to the maximum load can safely absorb more harmonic current without suffering severe voltage distortion. By enforcing TDD, utilities bypass the mathematical noise of fluctuating daily power consumption and regulate the exact volume of high-frequency pollution entering their infrastructure. Once engineers accurately quantify the distortion, they can install hardware to scrub the high frequencies from the system. The simplest solutions rely on passive electrical properties to blunt the pollution. Installing a line reactor directly ahead of a VFD adds pure inductive impedance to the circuit. Because impedance naturally increases with frequency, the reactor actively resists the sharp high-frequency current spikes, effectively smoothing the draw and suppressing the fifth and seventh harmonics. For more targeted scrubbing, tuned passive filters combine specific inductors and capacitors. These LC circuits act as a sink, tuned to a system's most destructive resonant frequency, trapping and absorbing specific harmonics before they reach the main grid. Moving beyond passive components, active filters function like noise-canceling headphones for the power grid. They monitor the line current in real time and inject an inverse, antiphase waveform that perfectly cancels out the targeted harmonic distortion. The most advanced mitigation happens inside the drive itself. An active front-end VFD replaces the standard diode bridge with IGBT transistors. This allows the drive to actively control the power input, drawing a near-perfect sine wave from the grid and preventing harmonics from being generated in the first place. Designing a mitigation architecture requires balancing the reliable, low-cost durability of passive reactors against the flawless precision of active electronics. Rather than relying solely on filters, engineers can also eliminate harmonics by altering the geometry of the power system using a multi-pulse configuration. A 12-pulse drive system requires a specialized transformer with 2 separate secondary windings, which then feed 2 parallel 6-pulse rectifiers. This setup utilizes a delta-Y transformer configuration to introduce a precise 30-degree electrical phase shift between the 2 secondary outputs. Because of this 30-degree offset, the 5th and 7th harmonic currents generated by the first rectifier are exactly out of phase with the harmonics generated by the second rectifier. When the currents merge at the primary winding, they naturally zero each other out. By tracking accurate TDD metrics and deploying specific mitigation topologies, facilities can utilize the precision of variable frequency drives without poisoning the upstream grid. Managing harmonic distortion ensures the thermal stability and physical longevity of the heavy infrastructure that powers global industry.
Thank you for viewing so far. If it gives you some information, hit the like button and subscribe for more such technical learning.